All right, we're going to look at Gauss's law, and it is an easier way actually to look at electric fields because what we're going to do is we're going to simplify a lot of the math by just using symmetry properties. In order to understand what Gauss's law is, we first have to understand what flux is, which is defined by the volume rate of flow. So think about this cup and imagine there's rain falling into the cup. All right, so that the direction of flow is into the cup. In its current position, we're going to get the maximum amount of rain to collect into the cup. If we rotate the cup, we can see that the amount of area to catch the water is going to decrease. So if you think about, if you just look at the opening of the cup, and you can see that the white area becomes less and less until you can catch no water in the cup. Now, this surface that we'll call like the plane of the loop of the cup has a vector component to it. And the vector points perpendicular to that flat surface. So that pen right there is representing the normal direction for that surface. What we can see there is when the normal is in the same plane, you get the maximum amount of flux, the maximum amount of water caught. If the normal is now perpendicular, since the rate is still into the page, it is now perpendicular with the normal, that's when we get the minimum. We're going to call the flux capital phi, all right? And there's flux for any rate of flow. If we were thinking about the rain, it would be the velocity of the rain and the area which it would be caught. But we're going to look at electric flux. So the rain is going to be the example, the physical example of what we would call the electric field. So in that situation, the electric field was going into the page and flowing through a certain area of opening, so that the flux is equal to the net electric field dot the area. Remember, dot products are when the vectors are parallel to each other, so we get the maximum when they're in the same plane, pointing in the same direction, and we get the min when they're perpendicular. So that flux is also the E times the area times the cosine of theta. And to get the net flux, we would sum up the E dot A for all surfaces, for all areas of the surface. The angle theta is the angle between the normal and the direction of the electric field. All right, so with that circular plane of the cup, the normal would be perpendicular to that plane. Some books will call it en roof. It would be a unit vector of 1, so it has no value, it just has the direction to it. So an example here would be we would have a surface, and we can have electric field going through it. If it's moving perpendicular, the normal would be in the same direction here, so the total flux through that would be the value of the electric field times the area times the cosine of 0, which would be 1, and that would give us the net flux through that object. If we tilt that object, so that the normal is now in that direction, but the field is still going this way, we would have to look at the angle between the direction of the field and the normal. So if that was 60, we would have the electric field strength times the area times the cosine of 60, which would be a half. So there we would get half the amount of flux that we would have gotten from the perpendicular example right here. If we have a three-dimensional object, such as a cube, we could have flux going through multiple surfaces. So here, let's make our electric field go along the x-axis, and because we have multiple surfaces, we will have multiple flux. So call that one side 1, side 2, side 3, side 4 would be the bottom. And I'm not going to be able to label the other ones so that we can see them, so I'm going to stop there. You can get the idea. So to find the flux through surface 1, it would be E dot A. Wrote the A first. And we would see that the electric field is perpendicular to that normal, but the normal is going to be pointing to the left for that surface. So therefore, the flux would be negative. For surface 3, the normal's pointing in the same direction, we would get a positive flux. All right, so this flux is negative, this flux is positive. So if we were able to just add those two up, we would see that it would be the same amount of field, the same amount of area. Those two would cancel each other out. If we look at surface 2, the normal is pointing perpendicular to the field, or none of that field is going through that area. So if there's no field going through the area, the flux for surface 2 is 0. The flux through surface 4 would also be 0. The flux through the back and the front would also be 0. The flux through the bottom would also be 0. So the flux is, there's only a flux through the side 1 and side 3, because those are the only two surfaces that are perpendicular to the field. So the net flux through this cube is going to equal 0, because 1 and 3 cancel each other out. The flux going into a three-dimensional object is negative. The flux coming out of a three-dimensional object is positive. Now, if we have irregular objects, we can't use a finite sum. So I just have some bag, say it's a bag and it's tied shut. So this has dimension to it. Okay? And over this surface, we have small sections of area, and they all have their own normals with the surface. If we had electric field going this way through that object, what we would have to do is add up the flux through every single little area. So when we have irregular objects, we have to integrate so we can add up every dot product, and it's infinite. Now, when it is a shape like this, we can't actually do the math, all right? But we can understand the concepts here. So it doesn't matter how many of those little areas are pointing in what direction. So the net flux through that shape is going to be 0, because whatever goes in has to be negative. Whatever comes out has to be positive. And if we were able to reshape that irregular shaped bag into a cubic shape, it would still, as we proved before, have a net flux equal to 0. Other idea is all of the electric field that goes in comes out. So there is no net electric field going through an area. It always goes out. So this is always going to be true when the field originates outside of the surface. Because we just have this field here. Something has to be creating it. It could be far away. We don't know anything about what is creating that field. So we're going to look at how this relates to Gauss's law in the next video.